Welcome to our discussion on the limit laws. Basically, we have a whole set of very intuitive, very obvious laws. It's not like other things like putting constants inside of a function and it going the opposite direction. These things act the way you think they should act. For instance, the first one says that if you have the sum, right, if you take the limit of the sum of two limits, if you take the limit of the sum of two functions, it's just the sum of those two limits. That's what this first one means, right? The limit of a sum is equal to the sum of the two limits. And then, of course, it works the same for the difference. The limit of a difference is equal to the difference of the limits. This one says that if we take the limit of a function times a constant, it's the same thing as the constant times the limit of that function. So you can basically take constants out of functions and then evaluate limits of what is left over. Again, it kind of does intuitively what we would hope it would do. Same thing with a product, right? The limit of a product is the product of the limits, and the limit of a difference, right, or a quotient is the quotient of limits. Of course, the bottom can't equal to 0. So they're all very intuitive. They work the way we would hope them to work, so it makes it very easy to kind of memorize them and work with them. These are the limits just restated in English. Let's look at some examples. We can use limit laws to now evaluate more and more complicated limits because we know we can break them down into these kind of basic pieces from these laws. If we're trying to figure out, for instance, this first piece, the limit of f of x plus 5 times g of x, we know that based on the rules that it's going to be the limit of f of x plus the limit of 5 times g of x, and then we can also pull the constant out, and I apologize, those are my really horrible limits. I know it looks like natural log, but I'm just too lazy to write it out nicely. And we know that by looking at the picture, as we approach negative 2, right, so as we're right here, this is x equals negative 2, the limit of f is up here, right, at 1, and the limit of g is down here at negative 1. So this is simply positive 1. Let me erase that. F is just 1 plus 5 times negative 1, or 1 minus 5, or 4. It's that simple. And the rest would be exactly the same way, except, at different places. Okay, so here's the first one all written out. Okay, what about the second one? We're taking the limit as x goes to 1. Well, if you'll notice, as x goes to 1, f is fine. We can take the limit of f of x as x goes to 1, right? Because as we get to this point here, f is approaching 2. But as we get closer and closer to 1, what's happening to g? From the left, it's approaching negative 2. From the right, it's approaching negative 1. So that means this one does not exist. So what do you think the product is? Well, hopefully you're kind of thinking, logically it makes sense that if one of them doesn't exist, then how could their product exist? And it doesn't, right? Even though this equals 2, when you try and look at them together combined, you get does not exist. Okay, and then we can look at the third example, looking at the quotient, right, this fraction, so to speak. We're going to look at what's happening as we go to positive 2, so we're now over here. At positive 2, it looks like f is, I don't know, about 1.4, almost 1.5, right? And then g, well, g looks like it's equal to 0. And so what's our answer? Well, you can't divide by 0, right? So this is another does not exist. Here it is where we're just talking about those where we know we can't do the limit as we're approaching 1 because we get two different limits, right? We have a left-hand limit and a right-hand limit that are different for G, so therefore the limit doesn't exist for G, and thus it doesn't exist for their product. In this one, we're revisiting the last one we did where the limit as x approaches 2 of g of x equals 0, which is perfectly legitimate. That's fine. The problem is now trying to take the limit of that quotient, right? That ratio doesn't work. If you try to take the limit as x approaches 2 of f of x over g of x, by the limit laws, that should just be 1.4 over 0, but we can't divide by 0. So, does not exist. Okay, with the product law, the fact that we know the limit of f times g is also the same thing as the limit of f times the limit of g, we can expand that. And instead of saying the limit of f times g is the limit of f times the limit of g, what if they were both the same, right? What if it was the limit of f times f? Then we know that it's the limit of f times the limit of f, and isn't that just the limit of f squared? And that's what this rule here, the power law, is telling us, is we can now take that and expand it out and do this n many times, and so now the limit of a function raised to a power is just the limit of that function and then that answer raised to a power. Okay, so if we know that the limit as x approaches a of f of x equals 3, then the limit as x approaches a of f of x squared just equals 3 squared or 9. A couple other ones that should be kind of a no duh, right? If we're taking the limit of c, where c is a constant, so now we're trying to take the limit of the constant function, well, that answer is just going to be c, because remember, what does the constant function look like? If these are our xy axes, then a horizontal line, that's y equals c. So no matter where you are, pick any x, right? Pick any a, and no matter where you get, the height's not changing. So it's always just c. And then the limit of x as x approaches a is just a. It also should feel kind of like a no duh kind of rule. But if you don't remember it graphically, you can remind yourself this is the line y equals x. And wherever you go here, right, whatever this distance is the same. So whatever a you choose, you're going to be at the same height. And that's why you take the limit as x approaches a and you get an output that is in fact a. Okay, we can put those two laws together, the power law that we had before and the limit of, x approaching a of x, just equaling a, and go, well, now that if we have the limit of x to a power, it's just going to be a to a power. And the nice thing about this thing is this allows us to take the limit of all polynomials very simply, because now if we're taking the limit of 3x to the fifth plus 2x cubed minus x plus 5, let's say we're taking the limit as x goes to, let's say, 2. Well, the limit laws tell us that we can take each of these pieces separately. So now we're just looking at 3x to the fifth plus blah, 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 blah. But then the constant law tells us we can take that 3 out. And so now we have 3 times the limit of x to the fifth, right? Plus blah, 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 all the other stuff. But then this power rule tells us that this is just going to be 3 times the limit of x to the fifth. as x approaches 2, and we know that when we're taking the limit as x approaches a number of just x, we just get that number, and so now we have 3 times 2 to the fifth. 2, 4, 8, 16, 32. 32 times 3 is 96 plus blah, 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 blah. We do that for all of them. So basically evaluating polynomials is very simple. You're just evaluating each piece. Well, roots, remember, are just powers in disguise. Isn't the square root of x just x to the 1/2 power? Isn't the nth root of x really just x to the 1 over n? So if 9 holds, 10 holds from that. Right? So it's going to seem like we're throwing a dozen rules at you, but so many of them are really folded in from previous rules that it all kind of goes back to those original 5. And those original 5 are all kind of based on very intuitive, kind of logical solutions. So everything's going to be built on that, and it should be fairly easy to kind of memorize these and work with them. Okay, and once we have 9 and 10, we can generalize even further, and instead of just x to a root or a power, we can now have f of x to a root or a power. Okay, all of this is leading us up to the biggest rule, the one that you're going to use the most, and that's the direct substitution property. Once you know all of these laws of limits, and you know you can use things and you can add them and you can subtract them, you can move them around, you can simplify them, and you can make your life easier and blah blah blah, do all that stuff. The nice thing also is to know that if we're taking the limit of some function at some point a, it will actually just equal the function evaluated at a as long as the function is defined for a. So anytime you have any function, here it just says polynomial or rational, but really this is true, but it's even more general than that. Really, if it's just any function, where f of a exists, then this is true. So whenever you're trying to evaluate a limit, the very first thing you should always try every time is just plug the number into the function. If you're evaluating the limit as x approaches 3, plug 3 into the function that you're evaluating and see what happens. If it comes out and it gives you a number, right, gives you an answer, then that's just your answer. That's the limit. If it doesn't, then you have to use other techniques. So in general, we know that if we have two functions that are continuous and equal, right, so f of x and g of x are the same everywhere except for at some point a, then the limit as x approaches a of one function is equal to the other. And where is this useful? Well, how about something as simple, and we've seen these types of things already. Take the limit as x approaches 1 of x minus 1 over x squared minus 1. Well, the first thing we want to try is the direct substitution property, right? So we just plug in 1 and we get f of 1 equals 0 over 0, and it doesn't work, right? We can't evaluate it. So this doesn't help us. But we know down here that, hey, if I know a function that's equivalent to this function everywhere except at 1, then maybe I can try it again. And by looking at this, you go, hey, wait a minute, this factors on the bottom, and then those cancel, and I get 1 over x plus 1. Well, 1 over x plus 1 and the original function are identical functions. They're algebraically equivalent. The only place where they're not the same is at this number here, because this function was not defined there, and this one is. Because if I plug a 1 in here, I get 1 over 1 plus 1, I get 1 over 2, which is a half. And because these two functions are equivalent everywhere except at that point of discontinuity, or at that problem child point, that one that doesn't seem to work, then I know the limit of this thing just equals a half, because that's what the limit of the new function equals. And that's going to be one of the biggest techniques you're going to use with these things. When you're trying to evaluate limits and you get division by zero, which you know is a problem, then you try to algebraically manipulate that function to get rid of that zero, and you know that the limit of the new function is equal to the limit of the old function, as long as you haven't made an illegal move, as long as you've done your algebra properly. Sometimes it's easiest to calculate limits by just finding the left and the right hand limits. Uh, it's rare, but it happens. So you do the one-sided limit, you do the other one-sided limit, and if they're the same, then you know the limit right at that point has to equal those two numbers. Last but not least, certainly not least, the squeeze theorem is the most important one for a lot of things you're going to be doing for the more advanced limits. The first 5 limit things are the most important things, and the last couple slides where we knew that if we reduce things algebraically the same, that's very important as well. Once we start getting into more complicated limits that we can't evaluate algebraically, we can't reduce them, we can't use any of those tricks, then the next line of defense is usually going to the squeeze theorem. And the squeeze theorem is based on theorem number 2 here, that if you have a function that is always less than or equal to another function, so that basically just means you have one function that is consistently lower, right, than the other function whenever you graph them. And remember that this is always just near some point. So you could have a function like this and then a function like this, right? This would be, let's say, this is f of x and this is g here. And it says f is supposed to be less than or equal to g. Well, f is obviously not less than or equal to g, but it is on this neighborhood, right? So if a was somewhere in between those 2 points, then this holds, and that's all that matters, right? Is that f is less than g in some small neighborhood around a, right? Where x is near a. Except, and it always is except possibly at a. It always doesn't have to be true at a, because remember, when we're dealing with limits, we don't care what happens at a, just what happens close to it. Okay, if that's the case, if we have this kind of relationship between the two functions, then we know we have the same relationship between their limits. Again, it's very intuitive, just like the rest of the limit laws. And by that theorem, we then bring in the squeeze theorem. And this just says, if we have 3 functions, one function that's always greater than or equal to g, and one function that's always less than or equal to g, again, on some neighborhood around a, and again, possibly not at a, right? It doesn't have to happen at a. It can, but it doesn't have to. Then, if we also have that the limit of f and the limit of h both equal each other at a, then the one that's in the middle gets squeezed and has to also equal that amount. And the best way to understand this is to look at a picture. So the green line is your h function, the blue line is your f function, the red line is your g function that is being squeezed in between those two. Now you can see over here g is not in between those two functions. It doesn't matter, because we're only concerned with it happening in some neighborhood around a. And in this neighborhood around a, the green line is always above the red line, which is always above the blue line. Above or equal, of course, because it looks like they all touch right there. And of course they have to touch, because the next piece we have to have after we get the whole, it's squeezed in between them, is that these two functions, h and f, have to merge, right? They have to come together and give you the same limit at this a. So the h function is coming down at the same time the f function is coming up. They meet at L, and because g has been defined to be stuck in between those, when they squeeze together, g gets squeezed at that same height, and therefore its limit is also equal to L at that point. And that's the squeeze theorem. It's also sometimes called the sandwich theorem or the pinching theorem, because that middle function is just getting sandwiched or pinched or squeezed between the other two functions. And we will use this theorem to be able to evaluate some limits of some functions that we can't evaluate directly, but we know that there is another function, a simple function that we know something about, that is always bigger than it around a, and another simple function that we know something about that is always smaller than it, again around a. And then we take the limit of those two, and if they both approach the same number, then we know that the function in between them has to also approach it. So these are all things we're going to be using to try and evaluate limits. The first thing you're always going to try is just plug in the numbers, see what happens. If that doesn't work, then you fall back on some of the limit laws and you move some stuff around, you do limits of sums, limits of products, blah blah blah, and see if that works. If that still doesn't help, then the next thing you want to try is probably doing some sort of algebraic reduction and see if you can reduce the limit to something else, and then again plug in a, evaluate it at that point, see if it works. If it does, that's your limit. The next line of defense, if none of that works, is to move on to the squeeze theorem. Later on, when we learn how to take derivatives, we'll also have L'Hopital's rule, and in fact L'Hopital's rule ends up being easier than the squeeze limit and really even algebraic manipulations a lot of times. So it kind of moves up into the number 2 position, and after you try just evaluating the limit at a by just plugging the number in, if that doesn't work, then the next thing you try is L'Hopital's rule, and then you kind of go on from there. So every time we start adding new techniques and new things that we understand how to do, we just reevaluate which one is the best, and it kind of moves up the line of the techniques we're going to use to try and solve different types of problems. So with limits, try to plug in that number first, see if it works. If it doesn't, the next thing you want to try is algebraically reducing it to something else and then plug the number back in. And if that doesn't work, your last line of defense, at least for now, is to try the squeeze theorem.